Welcome to today's Explainer. I am incredibly thrilled to have you here with us because, honestly, we're looking at something truly fascinating. Have you ever wondered how pilots handle extreme runway restrictions? Today we're going to break down the highly calculated, incredibly high-stakes procedure known as the short field takeoff. Okay, let's dive into this and see exactly what it takes to get an aircraft safely off the ground when you are quite literally running out of tarmac. Picture this. You're staring down the nose of your aircraft at a runway that feels, well, a whole lot more like a driveway. You've got just 1,000 feet of usable surface in front of you. To put that into perspective, that's less than 3 football fields to get a heavy, complex machine pushed up into the sky. And to make matters even more intense, there is a towering 50-foot obstruction looming right at the very end of that short stretch. So, how does a pilot manage this without completely breaking a sweat? It requires absolute pinpoint precision, and that is exactly the puzzle we are going to solve together today. Here is our simulated flight plan for today. We're going chronologically from the holding point to safely airborne. We'll hit the short field challenge, pre-flight vital checks, lining up for maximum length, the takeoff roll, and finally, clearing the obstacle. Section 1. The short field challenge. The physics at play. Because before we even touch the engine, we have to understand the environment we're operating in. You see, the physics dictating our takeoff length are wildly complex. A pilot has to account for 8 specific factors before even attempting a short field takeoff. We're talking temperature, density, pressure altitude, the aeroplane's weight, the exact condition of the runway surface, any slope on the runway, the headwind component, and general wind conditions. Every single one of these variables can drastically alter exactly how much runway we're going to need to get those wheels off the ground. So let's officially define what we're actually doing here. A short field takeoff, or SFT, is a maneuver carried out when your available runway length is seriously limited, or there's a high obstruction on your takeoff path, or, both. For our simulated scenario today, we are facing the whole shebang, a strict 1,000-foot runway limit and a 50-foot obstacle at the end. To pull this off, our flaps are set to the takeoff position right from the very start. Section 2. Pre-flight vital checks. Methodical precision. Now we shift gears into a calm, highly focused mindset as we sit at the runway holding point. Before we even think about asking for clearance, we absolutely must run through our vital actions checks, which are famously remembered by the acronym TMFISCH. Just look at the sheer volume of these checks. Trim set for takeoff. Throttle friction lock adjusted. Mixture rich. Ammeter checked 0 or positive. Aux fuel pump off. Fuel quantity sufficient. Flaps set for takeoff. All instruments checked. Switches as required. Magnetos checked. Controls free and correct. And finally, hatches and harnesses checked and secure. It really is a brilliant demonstration of a pilot's necessary thoroughness before moving an inch. With TMFSISH complete and flaps confirmed in the takeoff position, we have to clear the engine. And guys, this is a highly sensory, very physical process. You hold the aircraft firmly on the toe brakes. You pull that control column fully back. Then you open the throttle smoothly to 1900 RPM. You're literally listening and feeling the vibration to ensure the engine is running flawlessly, all while quickly checking the temperatures and pressures are normal. Once that's confirmed, you ease the throttle back to 1000 RPM. Our machine is perfectly primed and ready to go. Section 3. Lining up for maximum length. Every inch counts. So the crucial point is we need to capture absolutely every available inch of tarmac. Let's compare a standard procedure to our extreme short field procedure. Normally, you might just casually turn right for the lineup, but for a short takeoff, no way. That wastes precious space. Instead, we move all the way to the absolute very beginning of the runway to avail the maximum takeoff length possible. Ensuring no aircraft are on final approach, we continue straight and then commence a highly controlled turn using extra braking and sufficient throttle to line up directly along the runway centerline. We're literally operating on the edge. Coming out of that turn requires intense visual focus. As a pilot, you're looking forward, checking for the equal convergence of the runway on either side of the aircraft's nose. You absolutely must ensure your wingtips are perfectly equidistant from the runway edges. You inch forward just slightly to straighten that nose wheel, and then you stop the aircraft entirely. If you look back right now, you'll see we've used practically 0 runway distance for this lineup. Every single inch is saved for the run. Section 4. The takeoff roll. Building speed. We've got our departure clearance, and it's time to take control. Okay, here are the visceral, step-by-step physical actions of the roll.
First, you hold the control column in a neutral position while keeping the aircraft firmly locked on those toe brakes. Second, you open the throttle fully and smoothly, checking your static RPM and making sure temperatures and pressures are still in the green. Third, release the brakes. As soon as the aircraft surges forward, step 4 is absolutely critical. Use the elevator to take the weight off the nose wheel. Why do we do this? To significantly reduce surface friction, which lets the aircraft accelerate much faster.
All of this rapid acceleration is building toward our first major milestone, VR, or rotate speed. Now, even though we've taken weight off the nose wheel to reduce that friction, the wheel must be held lightly on the ground until we hit VR. As our airspeed increases down this tiny runway, our elevator is becoming more and more effective. We are waiting for that exact perfect speed.
And boom, there it is, 51 knots. The very millisecond the airspeed indicator hits 51K, we apply gentle backward pressure on the control column. The nose lifts, the wheels separate from the tarmac, and we are officially airborne, successfully lifting off well before we hit our 1,000-foot limit.
Section 5. Clearing the obstacle. The steep climb. We're off the ground, but we still have a massive 50-foot obstruction looming ahead of us.
The moment we're airborne, we actually need to lower the nose just slightly. This requires only a small decrease in back pressure rather than a noticeable push forward. We do this for a very specific reason, to allow the airplane to rapidly accelerate to VTOS, the takeoff safety speed, which is exactly 57 knots. Once we hit 57K, we lock it in and hold it. This gives us a much higher attitude and a steep angle of climb to safely carry us up and away from the danger zone.
But while we hold this steep climb, there's an invisible, deeply physical battle happening right there inside the cockpit. Because we're operating at a high power setting, combined with a very low airspeed of 57 knots, the aircraft naturally wants to pull hard to the left, a strong left yawing tendency. To counteract this and keep straight on our reference point, the pilot has to aggressively apply much more right rudder than normal. Honestly, it's almost like pressing your foot hard against a heavy, stubbornly closed door.
And this brilliantly illustrates our success. Let's look at the actual data of this precise procedure. As we approach the absolute end of the runway, the obstacle height is 50 feet. But because of our strict, unwavering adherence to VR at 51 knots and holding our steep climb at VTOS at 57 knots, our current altitude is 200 feet above ground level. That gives us a massive, comfortable, safe clearance margin of 150 feet over the obstacle. We did it!
Okay, take a breath. Now that we've successfully cleared the obstacle by a safe margin, the pacing in the cockpit can finally calm back down. But wait, we can't just retract our flaps immediately. 3 strict criteria must be met first. We must be at a safe height, we must have achieved a safe airspeed, and we must confirm a positive rate of climb.
Having met those 3 criteria, we retract the flaps and allow the aircraft to accelerate to our final target, VY, the best rate of climb speed, which is 80 knots. Once we hit 80 knots, we simply trim the aircraft to relieve those heavy control pressures. The maneuver is completely finished. And that, my friends, was a textbook short field takeoff.
We just took an incredibly complex set of physics, intense visual checks, and highly precise mechanical inputs and turned it into a perfectly safe 100-foot clearance over a looming obstacle, all from a runway barely long enough to even register. It really makes you appreciate the profound skill sitting right behind the yoke, doesn't it? So I want to leave you with this thought. The next time you look up and see a plane soaring effortlessly overhead, or the next time you take a flight yourself, what other invisible maneuvers and calculated masterclasses are happening right under your nose to keep you completely safe? Thank you so much for learning with me on this explainer today. I'll see you next time.